Vectors are represented as arrows in 2 space, which you probably recognize as 2-dimensional space, or 3 space being 3D. So these arrows have some initial and some terminal point. So we can denote the vector as a letter with an arrow on top, or the vector from a point P to the point Q as follows. So vectors have a length or a magnitude and a direction, unlike scalars or numbers which only have a magnitude. Now 2 vectors are equivalent if they have the same length and same direction. So as we can see, A is equivalent to B, but these vectors are not equivalent to C. So even if C had the same length as these vectors, it would still have a different direction. And a special vector, being the 0 vector, is a special vector that has the same initial and terminal point. We can add vectors using the head-to-tail method or the parallelogram method. So with the parallelogram method, when adding vectors A and B, we place their tails together and we construct the parallelogram from these vectors. So this line is parallel to vector A, and this line is parallel to vector B. And the resulting vector is drawn from the initial point of both vectors as the diagonal to the opposite end of the parallelogram. So that's our resulting vector C. So our resulting vector C is A plus B. And using the head-to-tail method, we can put the tail, or initial point of B, at the head or terminal point of A. And the resulting vector is drawn from the tail, or initial point of A, to the terminal point of B. So in this case, we have C is A plus B. And alternatively, we can place the initial point of A at the terminal point of B, and our resulting vector C is drawn from the initial point of B to the terminal point of A. So in this case we have C is B plus A. So as we can see in both cases, we have the same resulting vector C. So therefore vector addition is commutative. We can extend the head-to-tail method to add more than 2 vectors. So here we have A plus B plus C. So we can place the initial point of B at the terminal point of A, and the initial point of vector C at the terminal point of vector B. And therefore the resultant vector is drawn from the initial point of A to the terminal point of C. Now we can visualize this better by adding A and B first, using the head-to-tail method. And then adding this to C using the head-to-tail method again. So as we can see, our resultant vector is drawn from the initial point of A plus B to the terminal point of C. Now alternatively, we can add B and C first using the head-to-tail method, and then add A to this result, which gives the same resultant vector. So as we can see, vector addition is also associative. We can visualize vectors when we add them in 3D space or 3 space So using the associative property of vector addition, we can add A and B first using the parallelogram method. And then we can add this result to C. So again, using the parallelogram method, our resultant vector would look like this. Now alternatively, we could have put the initial point of C at the terminal point of A plus B, so it would look like this. And our resultant vector is drawn from the initial point of A plus B to the terminal point of C. So that gives the same result. Scalar multiplication, or the multiplication of a scalar or number with a vector, basically scales that vector. So here we have a positive scalar between 0 and 1. So effectively multiplying this with a vector is going to make it shorter. And if the scalar was greater than 1, then this vector would be longer, as you can imagine. But it still has the same direction. Now if we have a scalar of -1 multiplied by our vector, well, that just reverses the direction of our vector. And if we have 0 multiplied by our vector, that gives the 0 vector. We can take advantage of vector addition to subtract vectors. So if we want to subtract B from A, for example, then we can first negate B, as we've shown here, which reverses its direction, and then we can add this to A. So using the head to tail method, we place the initial point of minus B at the terminal point of A, which looks like this, and then we draw our resultant vector D from the initial point of A to the terminal point of B, using the head to tail method. So as we can see, this is not the same as B minus A. So in this case, we negated A and added this to B. So the initial point of minus A is placed at the terminal point of B, and our resultant vector is drawn from the initial point of B to the terminal point of minus A. So these do not give the same vector. And therefore vector subtraction is not commutative. Vectors can be conveniently represented in coordinate systems. So for example, in 2 space, or 2-dimensional space, the vector A has components A1 and A2, which in this case signifies the x and y direction. Now in 3 space, or 3-dimensional space, noting that there are also different coordinate systems in 2 space, such as polar coordinates, which are extended to 3 space as cylindrical and spherical polar coordinates. We'll generally visualize the vectors in 3 space using Cartesian coordinates. So here the vector would have components A1, A2, and A3 to represent the x, y, and z directions. And in 2 space, the 0 vector has the following components, and in 3 space, it has the following components. And 2 vectors, A and B, are equivalent if all their components are equal. So A1 is equal to B1, A2 is equal to B2, and A3 is equal to B3. And as we've seen previously, we can write A in matrix form. So in 3 space, we can represent it as a column vector or a column matrix, or also a row vector or row matrix. If we have a vector in 2 space, for example, where its tail is not at the origin, so suppose its initial point is at point P and its terminal point is at another point Q. Well, we can use special types of vectors that have the initial point at the origin. So these are called position vectors. So I'm going to call this vector 0 to P. And I'm going to call this second position vector drawn to the terminal point of Q as 0 to Q. So using the vector head to tail method, 0Q is equal to 0P plus A. So therefore the vector A is 0Q minus 0P. Now if we suppose vector 0Q has the components x2 and y2, and 0P has the following components x1 and y1, so therefore the components of vector A can be obtained as x2 minus x1 and y2 minus y1. And if you extend this to 3 space, you'll see that vector A has an additional component in the z direction.